All right. So what you've got can I help you. All right. So we're talking about adding probabilities, and do you remember the word when you're talking about counting and probability that means add?
And? Is it and? Or.
Which one? Or. Okay. Or means add, and means multiply.
Oh.
Okay. So let's think about this. If you were going to flip a coin twice, okay, and I want to know the probability that the first one is heads and the second one is heads. Okay? So let's think about this. Well, let's go the old way. Let's just list out all the things you could do. You could do tails, tails. You could do tails, then heads. You could do heads, then tails. Or you could do heads and heads. Right? How many outcomes are there? 4. How many of them are heads and then heads? 1. So the probability would be 1 out of 4. Remember, probability is ways to get what you want over total possibilities. Okay? Well, what is the probability that the first one was heads? 1/2. What was the probability that the second one was heads? 1/2. What you would do to get 1/4 is to multiply those. Okay? Because you want this and this, right? So what that's saying is half the time the first one would be heads, right? And then half of that, the second one would be heads. So half of a half would be 1/4 of the time you would get heads twice. Okay? See how that works and why it multiplies, okay? Well, or is a little different. What if I said, what's the probability that the first one's heads or the second one's heads? Okay, well, let's look at the 4 outcomes. How many of those is the first one heads or the second one heads?
1, 2, 3.
3. The only one that's not is that one, right? So, can you do something to 1/2 and 1/2 and get 3/4? No. Okay. So, did I lie when I said that it means adding? Because if you added, what would you get? 1/2 plus 1/2 is 1, which means that if anything has a probability of 1, it means it always happens. Well, it doesn't always happen that the first one said or the second one says. Okay? So here's the issue. Let's say that I put every restoration student's name in a hat, and I drew out a name. And I wanted to know what's the probability that that person is female or in the 10th grade. Okay? So or means I add, right? So would it work if so let's think of our 2 things. One is female, the other one is 10th grade. What would be wrong if I took everybody's name that was a female, added everybody's name who's in the 10th grade, and divided that by the total number of students? Why would that not work?
Because if everybody's female, we're already included.
Some people got counted twice,
Yeah.
right? Who got counted? The people that were in both groups, right? Okay. So here's or does mean add, except when it's possible that you could have been in both events. Okay? So here's the formula. The probability that A or B happens is the probability that A happens plus the probability that B happens, but we run into a problem if we counted any outcomes twice, right? So so this formula is not complete, okay? We got to decide how to modify it. But let's think back to the 10th grade girls example. If I wanted to know how many people were female or the 10th grade, if I took the number of females and added the number of 10th graders, what could I do to get the number of people that are female or 10th grade? Subtract how many 10th grade girls you have. Because those are the people you counted twice. And if you subtract it, you only counted them once, right? So what we do is we subtract the probability that you were both A and B. Does that make sense? So let's look at this. What is the probability that the first is heads or second is heads? So it's the probability that the first is heads, right? Plus probability that the second is heads minus what? What did we count twice? We counted twice if we got first heads and second heads, right? If you added up all the trials that the first one was heads and all the trials that the second one was heads, the one you counted twice was the one that both were heads, right? So minus the probability that both were heads. So now let's see if that gives us 3/4. What's the probability that the first one is heads? 1/2. Plus, what's the probability the second one's heads? 1/2. Minus, what's the probability that the first and the second is heads? 1/4. 1/2 plus 1/2 is 1. 1 minus 1/4 is 3/4. Does that make sense? Okay. Now, what if I change that a little bit and said, what's the probability that the first is heads or both are tails? Okay, well, according to our formula, that's A and that's B, right? So according to the formula, what would this be? It would be the probability that the first is heads, right? Plus probability that what? Both are tails. Minus what? Probability that the first is heads and both are tails. Right. So what's the probability that the first is heads? 1/2. Plus, what's the probability that both are tails? 1/4. Minus, what's the probability that the first one is heads and both are tails? 0. Right? If the first one is heads, then they can't both be tails, right? Okay, so that a special circumstance comes into play. These are two events that cannot both happen, right? If the first one was heads, there's no way that they're both tails. If they're both tails, there's no way the first one was heads, right? So if you ever have two events that cannot happen, they are called mutually exclusive events. They can't both happen. Okay? So let's go back to the example where I was drawing names out of a hat. Mutually exclusive events would be the person is in 10th grade and the person is in 11th grade. Okay? If I wanted to know the probability that the person was in 10th or 11th grade, I'd take the probability they were in 10th grade plus the probability they were in 11th grade minus the probability they were in 10th and 11th. Well, those are mutually exclusive, so it doesn't make sense, right? So your book actually teaches you two different formulas, one for when they're mutually exclusive and one for when they're not. But I'm a big fan of memorizing as little as possible, okay? So this formula you can always use. Just what's going to happen if they're mutually exclusive? That's going to be 0, right? So what your book does is give you that formula for when they're mutually exclusive and this formula for when they're not. But you can use this one every time if you realize that is 0 when they are mutually exclusive. Does that make sense?
Yeah.
Okay. So if you're looking through your book and you see a formula without this, that's where that came from. If you know you're talking about mutually exclusive events, your book leaves this part off. Okay? But to me, just use this formula every time and you'll realize when they are mutually exclusive, this part is 0. Okay? Because if you think back to our example, if I wanted to count everyone who was in the 10th or the 11th grade, so I took everybody that was in the 10th and added everybody that was in the 11th, did I count anybody twice? No, so there's nothing to subtract away. Okay? Whereas before, when we were doing girls or 10th grade, I counted a group twice, so I had to subtract those away. Right? Okay. So, let's look at some examples. Okay, a marble is selected from a bag that contains 5 blue marbles, 2 red, and 3 white. What is the probability? So you're going to just draw one marble. What is the probability that it is blue or white? Okay, so in words, what goes in the formula? So it's the probability that what? Is blue plus the probability of what? That it's white minus the probability that it's blue and white. Well, what's going to happen? Can't be blue and white. So that's 0. Okay? So what's the probability that the first one is blue? 5 out of 10 or 1/2 plus what's the probability that it's white? 3 out of 10. You add those, you get 8 out of 10, which is 4/5. Okay? So let's do one that's a little harder. Okay? A letter is chosen at random from the alphabet. What is the probability that the letter is in the word glass or slower? So I'm wanting the probability that it's in glass or slower. So first, let's just fill in the formula. What would that be? Probability that it's in glass plus, because the word or, probability that it's in slower minus what? That it's in glass and slower. Okay, so if you chose a letter at random, what's the probability that it's in the word glass? Well, there's 26 letters, right? How many of those letters are in the word glass? 4. Why is it not 5? Yeah, S is there twice. So, I mean, if you draw an S, you don't get 2 points. You got a letter that's in there, right? So there's only 4 letters in the word, 4 different letters in the word glass, right? So it's 4 out of 26 plus how many letters are in the word slower? How many different letters? 6 out of 26 minus how many letters are in glass and slower? L
9
and S, right? So 2. The only letters that are in glass and in slower are L and S.
Oh, I thought you meant.
No.
Okay.
Does that make sense?
Yeah.
Okay. So that's 10 minus 2. That's 8 out of 26, which is 4 out of 13. Okay. So here's a tough one. But I believe in you. All right. There are 5 boys and 6 girls. 6 girls on yearbook staff. A committee of 5 people is being selected at random to design the front cover. What is the probability that it will be at least 3 boys? So you're going to have a 5-person committee. What is the probability that it has at least 3 boys? Okay. First thing you need to do is to make that a statement that uses the word and or. So that's another way of saying the committee has at least 3 boys. Using the word and or. 3
or more.
Okay. What's the more?
3 or 5.
Or 4. So what we're wanting is the probability that it has 3 boys or 4 boys or 5 boys. Right? Now, I didn't tell you how to extend the formula to 3 things, right? Well, I'm going to tell you now. All right, so we'll come back to that. If I wanted the probability of A or B or C, it is probability of A plus the probability of B plus the probability of C minus, now you only have to do minus if they're not mutually exclusive, right? If you're mutually exclusive, you didn't count anything twice, right? Well, what you counted twice is anything that was A and B minus anything that was B and C minus anything that was A and C. Does that make sense? Anything that was in both A and B, you counted twice. Anything that was in both B and C, you counted twice. And anything that was in both A and C, you counted twice. But if the three events are mutually exclusive, you can take those three off, right? So, are these mutually exclusive? If the committee has 3 boys, can the committee have 4 boys? No. If it has 3 boys, it has 3 boys and 2 girls, right? If it has 4 boys, could it have 3 boys? No. Could it have 5 boys? No, it has 4. So these are mutually exclusive. So it's just going to be the probability of the first one plus probability of the second plus probability of the third. Okay? So that's the probability of 3 boys plus probability of 4 boys plus probability of 5 boys. Okay? All right. What is the probability of 3 boys? Well, what we need to remember, probability is going to be the number of committees that have 3 boys over the total number of committees, right? Well, how many committees have 3 boys? Well, if you wanted to have 3 boys, you've got 5 to choose from, right? And you're going to pick 3, right? So that means it's the combination of 5 choose 3, right? Times, you got to pick 2 girls. So that's the combination of 6 choose 2. Now, why did I multiply them?
Because
And. We want 3 boys and 2 girls. So you do the probability of 3 boys, or the combination of 3 boys, times the combination of 2 girls, divided by how many committees are there? That's the combination of 11 choose 5. Right? Plus, what's the probability that it's 4 boys? Well, that's going to be the combination of 5 choose 4, right? Times, well, if we've got 4 boys, we're just going to pick 1 girl, right? Combination of 6 choose 1 over combination of 11 choose 5. Angelo, you need to not be working on other classes. All right? Probability that it's 5 boys. Well, what's that going to be? Combination of 5 choose 5, right? Times combination of, we're not going to pick any girls, 6 choose 0 over combination of 11 choose 5. Or you could use common sense here. How many 5-boy committees are there?
1.
Just 1. And if you do that top, you're just going to get 1. That's going to be 1 times 1. Okay? So, what is the combination of 5 choose 3? Well, that is going to be combination of 5 choose 3. Remember, the formula is 5 factorial over 3 factorial, 2 factorial.
Yeah.
Mm-hmm. So that's 5 times 4 times 3 factorial over 3 factorial times 2 times 1. 2 goes into 4 2 times. 5 times 2 is 10. So that is 10. What's the combination of 6? Choose 2. That's 6 factorial over 4 factorial 2 factorial, which is 6 times 5 times 4 factorial over 4 factorial times 2 times 1. 2 goes into 6 3 times. That's 3 times 5 is 15. Over, what's the combination of 11? Choose 5. Well, that's going to be 11 factorial over 6 factorial 5 factorial, right? Which is 11 times 10 times 9 times 8 times 7 times 6 factorial over 6 factorial times 5 times 4 times 3 times 2 times 1. Okay, 5 times 2 is 10. 4 goes into 8 2 times. 3 goes into 9 3 times. So, Brittany, what is 11 times 3 times 2 times 7? Actually, I got it right here. 462, yeah. Plus, we know that both or all the bottoms are going to be 462, right? And this one was 1 at 462. So we just got to figure out this middle. Okay? So, what's the combination of 5? Choose 4. Well, that is 5 factorial over 4 factorial 1 factorial, right? Which is 5 times 4 factorial over 4 factorial times 1, which is just 5. Now think about that. Don't throw out your common sense. If you've got 5 guys to choose from, how many groups of 4 can you make? Well, if you're picking 4 people, how many people are you leaving out? 1. So this is really saying how many different 1 people can you leave out? 1 person. So there are 5 people you could leave out. So there are 5 different groups. Make sense? Okay. So this is 5. All right. Use common sense here. If you have 6 girls to choose from, how many 1-person groups can you choose? 6. Now, if you get bogged down in the work and you forget that and you want to plug it in the formula, that's 6 factorial over 5 factorial 1 factorial, which is 6 times 5 factorial over 5 factorial times 1, which is 6. Okay, but common sense helps. Okay, so now we have 150 over 462 plus 30 over 462 plus 1 over 462. So that is 181 over 462. I change. Okay? So let me let y'all do one. So you draw 2 cards out of a deck, right? what is the probability that they are both red or one hold on. At least one heart. Okay. I made this one harder than I wanted to, so I'm going to walk through it with you. Okay. Well, let's first just plug it into the formula. So, what would it be? The probability of what?
Both red.
Probability they're both red plus probability at least one heart minus what?
Red.
Probability that they're both red and at least one heart. Right? So, what's the probability that both are red? Well, if you're only picking from the red cards, it's the combination of 26 choose 2. Right? Because I want to know how many 2 cards you could pick that are both red. Hold that. Well, if they both have to be red, it's just out of the red. But the whole deck is the combination of 52 choose 2. Right? Plus at least one heart. You've either got one heart or both hearts, right? So that becomes the probability of one heart plus the probability both hearts, because that's an or, right? And you don't have to do minus anything, because if there was only one heart, it can't both be hearts, right? Minus this junk. Okay, so what's the probability of one heart? So I'm going to leave this. Well, it would be, on the bottom, we got this, always. So we're going to pick one heart out of how many? 13 hearts, right? So that's the combination of 13 choose 1 times how many cards are there that are not hearts? 39. Because there are 52 and 13 of them are hearts, so there are 39 that are not, right? And we're going to pick one from those. So it's the combination of 39 choose 1. Right? Plus, probability that they're both hearts is the combination of 13 choose 2 over combination of 52 choose 2. Minus this, and means you multiply, right? So that's the probability that they're both red, which we know already, right? Times at least one heart, which would be this or this, right? Okay. I'm going to scrap this. This ended up being a lot harder than I meant for it to, and it's a lot harder than anything that's going to be on your test. Okay? That's what I get for making up problems as I go. Okay? We could get there, but it would just stress y'all out and take up the rest of the class. Okay? So, sorry. All right. Okay.
Yeah, that was gonna take a minute.
Okay.
That kind of gave me a headache.
I'm sorry. Again, sorry. Okay. Sometimes until you're working them out, you don't really know how difficult a problem is. Okay. So let's say that there is a school. Here's an easier one. Okay. And that this is how the 10th and 11th grade are broken up. Okay? So, if you chose someone at random, what's the probability, and we'll use back the example we've been doing, 10th grade or a girl? Okay, well, according to the formula, what is that? It's the probability that it's a 10th grader plus probability that it's a girl minus what? Probability that it's both 10th grader and a girl. Okay, so that adds up to be 40. That adds up to be 42. That adds up to be 48. That adds up to be 34. So those add up to be, there are 82 total students. Okay? So what's the probability that you pick someone at random and they are a 10th grader? How many 10th graders are there? 40 out of 82. Right? Plus, what's the probability you chose a girl? 34 out of 82. Minus, what's the probability that you chose a 10th grade girl? 24 out of 82. This is more the caliber of question. Okay. So then that becomes 74, so 50 out of 82, which is 25 out of 41. Make sense? All right. Let me give y'all a worksheet, and that will be it for today. Hold on one second.